here tonight. This is such an important event for our organization and for the campus. As you heard in talking about the awardees, emeriti are a critical part of the fabric of UCLA. Retired doesn't mean you're off and gone, and you're all my models and heroes because I'm new to this whole retirement thing. Only 1 year in, but I'm figuring it out sort of slowly. But you know, the extent to which you're engaged in simply getting together, strengthening community, teaching still, mentoring still, doing research, and just showing up, being a champion and cheerleader for this incredible institution that had such an important impact on our lives, and you in turn on the institution. These are fragile, difficult, confounding times that I don't think any of us could have imagined. And in fact, every day you wake up with something new that it's like, what is that about? And UCLA is depending not only on the staff and faculty and alumni, but on us to help continue to strengthen the university's mission, to keep the faith, to keep the optimism, but also to be vocal advocates and proponents. And that comes not from just a place of passion and love and history, but from knowledge. So these events, like tonight, are a chance for us to learn more. So we're going to have a conversation. It's going to be in 2 parts, led by our Director of University Conversations, Stuart Wolpert. And I'm delighted that Dino Di Carlo, my colleague in Bioengineering, is here today. And the 2 parts are first to talk about some of the research and discoveries that have been going on in his lab. You know, he's had an incredible impact on the department, and his research is highly intersectional, not just engineering, but intersectional with medical school, with healthcare delivery. I mean, really, it's incredibly broad in its import and incredibly innovative in how he conceives it and how he guides his students in multidisciplinary training, launching them into amazing careers. And then I know they've gone into a wide range of things, from academic to entrepreneurship. So the first part, he's going to tell us a little bit about his research and the impact it's had and its potential for even more going forward. And the second part, he's going to talk about some ideas that he's expressed out in public square about how universities like ours can face, are facing, and will not just survive but thrive through the turbulent seas on which we find ourselves. So with no further ado, I'd like to welcome Stuart Wolpert, who will introduce Dino Di Carlo. And they'll be joining us.
Thank you very much, Robin. Delighted to be here. And I'm delighted to introduce Dr. Dino Di Carlo, UCLA Professor and Chair of Bioengineering and Professor of Mechanical Engineering in the UCLA Samueli School of Engineering, and a member of both the California NanoSystems Institute and the Jonsson Cancer Center. Dr. Di Carlo is a world-renowned UCLA professor, inventor, and entrepreneur who has made key innovations in biotechnology, co-founding 5 startup companies. He holds UCLA's Armond and Elena Hairapetian Chair in Engineering and Medicine. His laboratory has generated more than 80 U.S. patents. Is that remarkable? 5 startup companies, 80 U.S. patents. We're fortunate to have him here. Dr. Di Carlo is an elected fellow of the International Academy of Medical and Biological Engineering, the Royal Society of Chemistry, and American Institute for Medical and Biological Engineering. And he's the recipient of many awards, including from the National Science Foundation, the National Institutes of Health, and the David and Lucille Packard Foundation. Dr. Di Carlo was honored at the White House with the Presidential Early Career Award for Scientists and Engineers, the highest honor bestowed on young scientists and engineers by the U.S. government. Please join me in welcoming Dr. Dino Di Carlo. Delighted to have you here, Dino. Delighted to have you here. We're going to talk about science soon, but before we do, let's start with literature.
Elements of society today, and it's a challenge that we have to overcome. You know, the thought was that literature like this was to help us prepare and not repeat these things, but of course, history repeats, right?
So in the second half of the program, we're going to talk a lot more about the impact of these deep federal cuts in research. But now let's talk about your research, about several of your research projects. Lyme disease can be debilitating, leading to inflammation of the brain and heart and problems with memory, hearing, and vision that can last for years. Lyme disease affects more than 500,000 people in the U.S. each year. To detect Lyme disease, the Centers for Disease Control and Prevention recommends 2 tests at centralized laboratories. Results take more than a week, and the testing misses many, perhaps most, early-stage cases. But you and colleagues at the California NanoSystems Institute have developed a new testing technology similar to tests for COVID that provide results within 20 minutes instead of a week, 20 minutes. And you'll see as we talk more about Dr. Di Carlo's research that a lot of what he's done is really speed up everything where things can now go 100 or 1,000 times faster than they could before. But in this case, 20 minutes instead of more than a week. So you published this research last year in Nature Communications. Tell us about this research and whether you think it can lead to earlier treatment of Lyme disease.
Yeah. So the challenge with Lyme disease is that the current test, it's actually not one test, it's called a 2-tiered test. So you have to take a first test. If that result is positive, then you send your blood for a second test. That has to happen at a central lab. That's what the CDC recommends now. And it's, as you said, very costly. It takes a lot of time, and it can delay treatment. But actually, that's really important because there is treatment for the bacteria that causes Lyme disease. That's an antimicrobial, but you want to give it early before that bacteria can kind of hide in joints and other parts of the body. And maybe some of you in the audience, or you know folks who have suffered from chronic Lyme disease, and it's really something that you cannot. You never cure. You always will have that. So it's really important to do a test, to have a test that can be rapid and that you can then, the doctor can provide the right drug to you at the right time. Now, we're all familiar with the COVID tests that we took, these lateral flow assays that they're called lateral flow assays, but basically paper-based tests, like the pregnancy test. They're very rapid, they can be very cost-effective. And that type of technology, it's been around for a while, and it's really helpful. Now, that works well for a disease where you're looking for one particular marker. But in Lyme disease, we're actually looking at the immune response. Like, we're looking at how your immune response is to the infection, right? So we're looking for antibodies, IgM antibodies, and IgG antibodies. And each person's immune system is different. And so we had to come up with a new type of test that could detect an array of different antibodies that your immune system produce, targeting different parts of this pathogen. And using machine learning, we could look at an array of these spots. So instead of one spot on one line on your COVID test, we actually have many, many spots in the array. And we could read that array of spots and identify, different types of immune reactions and which were positive and which were negative, and train a model to understand that in a single test. So rather than the 2 tests that were required before, we call this a single-tier test. And because it uses the paper-based tests like the COVID test, it can be very rapid. And so this is very exciting, and we're now kind of continuing the development so that we can do these tests from the small finger pricks of blood. Potentially, you could do it at home eventually, or in a camp, or if your children are out, or anyone's out in the woods where you have more exposure to ticks. Luckily, we have less ticks in the LA area than kind of the Northeast, but it's also around the world. Lyme is prevalent across the world, usually in the Northern Hemisphere.
And what's the impact of the research? Does it imply that people who have Lyme disease can be identified and detected sooner and then treated sooner and more effectively?
Yeah, so you know, the goal is that you would be able to have this test, be able to take the test within 20 minutes and know you have Lyme disease. Maybe communicate with your doctor through a smartphone app, and then the doctor could prescribe you that drug right then, and you could take it before before it progresses too far.
And is this close to occurring?
We just started a company that is looking to commercialize this, and actually one of the founders of the company is an undergraduate student here at UCLA. That she had Lyme, and she actually also started her own nonprofit to help communicate about Lyme disease to folks. And so she's a really advocate to making these things come to reality.
Wow. Your team and colleagues at Columbia University published another study in Nature Communications last year that may lead to improved recovery following a heart attack, healing damaged heart muscle. Can you explain the tiny nanovials that you and your colleagues developed and walk us through this important study and its health implications?
Yeah, so let's start with the disease, which is, in this case, after a heart attack, you get remodeling of the heart tissue, you get scar form, and that leads to eventually heart failure in most patients, right, where you're not able to pump enough blood with your heart. So what you really want to do is to heal, regenerate that tissue after the infarct, after that heart attack, after the vessels occluded. And so one of the ways to do that is actually deliver cells that produce regenerative materials. And one our colleagues have studied for a long time is these regenerative, what are called extracellular vesicles, or EVs, but basically little fragments of cells that can contain proteins, they can contain other programming instructions for the cells that receive them. And actually, it's an interesting, many of you may know this, but these extracellular vesicles are relatively recently discovered as being one of the communication modes in which cells talk to each other. Right? So we've known for a long time that cells secrete things to talk to each other. We know that they touch each other to talk to each other. But relatively recently, they create these little packets of information, and then they send those out to talk to each other. It turns out to be a really good way to talk to another cell, because you have lots of information you can put in this little packet, and it doesn't get degraded by all the things around the blood. So that was the starting point. Now, let's say we want to make cells, or we want a therapy that has cells that produce these little extracellular vesicles, and lots of them. Well, how do we identify cells that produce lots of these vesicles? That was a challenge. So we had to develop a technology, we call them nanovials. You take your cup on your table, that little blue cup. Now imagine that is the size, the thickness of your human hair instead of that size, and we can make millions of those little cups. Like little test tubes for single cells. So each of those nanovials, we can put a cell in. We can then collect all the things that it secretes inside of that cup. And then so we can associate what it secretes to what that cell is there. And then we can sort out the cells that secrete lots of these little EVs from the cells that produce very few. And now we can start to identify what makes that cell unique. Why does it produce a lot of these EVs? Can we engineer cells to produce more of them? Or can we just select the most therapeutic cells that produce the most of these? And so that's what we were able to do. And what we found is that if you select the ones that produce more, and you give that to an animal that had a heart attack, and you give those cells, that it actually regenerates the tissue, and those animals have improved heart function.
And you think that would be the case in humans as well?
So, of course, a mouse is not a human, and there's a lot more that has to be done. We did get funding we had funding that was actually to Columbia initially, then Columbia was targeted, so it was canceled. And then Columbia made their deal or whatever. They received the funding. We haven't received the funding yet, maybe because we're canceled for a little bit.
So we don't know.
We'll see. We'll see. Yeah, we're going to do porcine studies, so pig studies, and then go to humans.
Fascinating research. Let's talk about a few more. You, Owen Whitty, and colleagues discovered 3 previously unidentified, naturally occurring T-cell receptors that target prostate cancer, and you developed a method that filters T-cells based on the receptor proteins found on their surface and the type and amount of immune response triggering molecules that they secrete. This research also used nanovials, that you just talked about, and could ultimately lead to new tumor-fighting immunotherapies. And other researchers can also apply your new technique. Tell us about this research.
Yeah, I think this is super exciting because if you think about where the cutting edge of therapies for cancer, autoimmune diseases, and almost anything we call immunotherapies, is that we can use cells themselves, or your own cells, your own immune cells, as therapeutics that can seek out particular tumor cells and then selectively kill them or selectively bring in other cells to kill them. We have, many of you have heard of this California Institute for Immunology and Immunotherapies that's starting up in where the old West Side Pavilion was, the UCLA Research Park. A big focus in that center will be these types of immunotherapies.
Are you part of that?
I am, so no one is part of that yet, but
Or will you be part
I
of it?
am part of the advisory committee that's helping to make sure that UCLA is part of that. And Owen, you can talk to Owen for more about that. But yeah, so really exciting class of technologies. And you think about, just from first principles, a cell is a kind of a machine that, a little nano machine that can think, right? It doesn't think like us, but it has an ability to process information. And so it can, it can kind of seek out particular parts of the body, and it can selectively release payloads to kill something only in a certain environment. Now that's something that's very difficult to do with like a chemotherapy or a antibody even, or other types of therapeutics that we have. So if you think about where the future is going, that's one of the key pillars that we're going to have in medicine going forward is how cells as therapeutics. But some of the challenges with making these therapeutics is the one that we tackled was on recognition elements. So you need the cell to have a way to recognize its target, recognize whether it's a tumor or not. Now, one way to have a recognition element is what's called this T-cell receptor. So that's our normal immune system, T-cells recognition element. But finding T-cell receptors that are specific to particular proteins that are different in a tumor, that's really challenging. The best way to do that is just to test many of these receptors, right? And so we found a way that we could test them, not just by how they bound to the target, to the cancer, but when they bound, did it make the T-cell produce all of these secreted things that are needed for it to kill the tumor cell and to bring in other cells. And so what we call this is a functional screening approach, not just does it bind or not, but it binds and then all the T cells all ready to go and be killed. So that allowed us to screen in a really robust way, and that allowed us to find kind of these new T cell receptors against prostate cancer, which were very effective. And we've extended that now with other collaborators, Li Ying and others, to new T cell receptors against, it's interesting, the cancer cells can present these peptides, which are parts of their antigens that they produce, but they can also present metabolites. So cancer is, notoriously, it proliferates and it has high metabolism. And so those cells, they can be recognized based on that high metabolism.
Wonderful research. Your research team devised a method for producing intricately shaped hydrogel microparticles at a rate of more than 40 million per hour, at least 10 times faster than the standard approach. Hydrogel microparticles hold promise for a range of uses in biomedicine, including for repairing tissue and as vehicles for delivering therapeutic drugs. Tell us about this research and its potential implications.
Yeah, and this connects also to these nanovials, because these nanovials are actually little hydrogel particles. So if you want to make millions of little test tubes, we need a way to produce them fast and cheaply, right? So we have to develop what we call microfluidic technologies to do that. And Robin knows all about microfluidic technologies, so awesome to see all of her work in the digital microfluidic space too, which we also are interested in. Yeah, so the other uses of these hydrogel microparticles are, as you mentioned, in wound healing, and regenerating tissue, or even aesthetics and fillers, or to reinforce after surgery tissues. And so that's been one of the directions. If you can create these hydrogel particles that form, you can kind of put as these kind of clusters of little spheres that are about the size of a cell. So you can imagine, if you imagine like packed gumballs all together, there's all these little holes in between the gumballs. And that's really important, so we can create like this type of pack of hydrogel particles in a wound. You have all these little holes so that cells can migrate in, and now they fill this space, and you can regenerate the tissue rather than having kind of scar formation. So I think there's applications in scaling up biological research in kind of these regenerative tissue engineering applications.
Scientists have known that circulating tumor cells in the bloodstream have the potential to provide vital information about a patient's specific cancer. But until research by your team, scientists and doctors could not reliably access information on how the cells behave. You and your team created a fast, effective mechanism to measure how these cells perform functions that drive the disease, such as producing proteins that degrade tissue. Tell us about this important research.
Yeah, and this is also, almost all of these, this is work that's collaborative across UCLA, which has been an amazing part of being part of this community. It's just so much high-level research across all different spaces. And this was a collaboration with Matt Redig's lab. He's in urology and works in prostate cancer. And also, I think Steve Dubinet's as well, and a few others. So,
Medicine.
Yeah. So it was a really collaborative effort where we had patient samples that we're getting. We look for, so let me first mention what circulating tumor cells are. So when we have a tumor, that tumor, when it becomes really dangerous is when it starts to metastasize, right? It goes to other parts of the body. And in that process, or one way that it does that is by releasing cells into the bloodstream. And if we can identify those cells, we call them circulating tumor cells. That's not a good sign if you have those, but if you can isolate them, you can start to perform what we call liquid biopsies. So we don't have to biopsy the tumor, we can take these cells from the blood to get information about the tumor. Right? So that's an advantage, and people have been starting to do this to look at genetic information about the tumor. But what we added on to that is, can we look at the functions of these tumor cells? And one particular function, these tumor cells that secrete enzymes that degrade tissue, those are probably cells that are very dangerous because they can invade into tissue, right? And they can also cleave off parts of proteins on their surface that allow immune cells to recognize them. So we don't want those types of cells. And so we were able to kind of develop an assay that isolated these cells and then characterized their function, this protein cleaving function, and to categorize. We found that could help us categorize patients that were going to do poorly versus not poorly.
Remarkably important research. Congratulations. Your research team also developed a tool that measures the physical strength of individual cells 100 times faster than competing technologies. This advance could make it easier and faster to test and evaluate new drugs for diseases associated with abnormal levels of cell strength, including hypertension, asthma, and muscular dystrophy. Tell us about this research.
Yeah, and you can see there's a theme here. We like to build different tools, right? That
Faster
allow us
than
to
anybody
faster,
else.
better, cheaper at NASA. So the point here is that all of our cells in our body, they contract. Like it's very easy, like your skeletal muscle. But even you have smooth muscle in your gut, you have your heart. All these cells contract. But actually, every cell in your body has contractile machinery. Has the ability to apply force. And even weird cells, like these cells in your eye called trabecular meshwork cells, that control the intraocular pressure. So if you have glaucoma, it's because of those trabecular meshwork cells. They're not allowing enough fluid out of your eye because they're too constricted. They need to relax. So almost every cell applies force, as airway cells for asthma, etc. There wasn't a great way to measure how much force a cell was applying at scale, right? So if we want to develop drugs that change the amount of force the cell applies, let's say for asthma, we want these drugs that relax the airway smooth muscle, right? So that the person can breathe. My son, when he was young, he had what's called reactive airway disease. Anytime he got sick, all of his airways would constrict up. We would go to the emergency room, go here to the UCLA emergency department. They knew us there at some point. And that was really scary, right? So what that meant is that their current drugs were not sufficient, right? The current bronchodilators only worked for a short period of time. Then you get adaptation. Your cells start to adapt. They say, okay, well, I'm going to contract again early. So we need new drugs for things like asthma, reactive airways disease, etc. Now, not many ways to screen for drugs that cause force generation. There's really no tools for that. So we had to develop a tool, and maybe just a simple description of this tool is you take a sheet that's flexible, put little patterns on it that I can put little cells on, and then tag those patterns. And when the cell contracts that sheet with the pattern on it, the pattern shrinks, and you can measure that. So that was a way that we were able to scale the measurement of cell force across huge numbers of cells, screen drugs. We started a company, Foresight Biotechnologies, that has done that drug screening and has identified a few compounds that are that look really promising for things like fibrosis, like lung fibrosis.
Wow. Approximately 1.7 million Americans each year pick up a nasty infection at a hospital or medical clinic, resulting in nearly 100,000 people who die from infection-related complications, and approximately $30 billion in direct medical costs. The biggest culprits, accounting for 2/3 of these infections, are medical devices like catheters, stents, heart valves, and pacemakers, whose surfaces often become covered with harmful bacterial films. You and Professor Richard Kaner developed a novel surface treatment that could help improve the safety of these devices and ease the economic burden on the healthcare system. I'd love to hear about this research.
Yeah, so the big problem here is that when bacteria get onto kind of these artificial surfaces, they start to form what are called biofilms. So they form they kind of spew out all sorts of sugars and other things to create this little nasty mess that is difficult to pull off, right? And so these biofilms are really what's the cause of all these kind of catheter-related infections and other things. And it's interesting because things like ethanol or like, if you try to flush it, those actually trigger more biofilm formation. So the cells get activated to trigger the biofilm formation. Rick's lab developed this really cool material called a zwitterionic material that has positive and negative charge that could be coated on these surfaces that prevented the attachment and biofilm formation. And so I think not only that, but it was inexpensive enough to do that coating in a repeatable way. And so now they're off to the races and trying to convince a lot of these medical device manufacturers to incorporate this into their...
Yeah, how's that going? Is it being used?
We were just talking to them on Saturday. It sounds like they have some really good results with it in the hospital settings already. and they're just they're trying to get more of the companies to adopt it.
There's more and more that could help a lot of people. I just learned tonight that you're incorporating AI in your research. Tell us about this.
But yeah, everything is AI now, right? So, I think I've been working in the microfluidic space, as broadly known as, where a lot of the work has been in the past about how do you miniaturize reactions, how do you automate reactions so that you can lower the cost or do something with less volume. We're at a stage now with the AI tools, large language models, foundation models, where we think that you can start to infuse intelligence into some of these automation steps of microfluidics. And the goal there is really to make sure that we have high-level scientific goals that are laid out by the scientists, and kind of the lower-level goals and maybe quality control and error correction can be done in an automated way by these types of AI systems. And so we've shown some proof of concept of being able to do that. Ability of these systems to also understand natural language and convert that natural language into motions or actuations of microfluidic devices.
How much federal research support has your laboratory received over the last 2 decades?
I think it's about 15 million.
Right,
Yeah.
right.
The other uses of these hydrogel microparticles are, as you mentioned, in wound healing, in regenerating tissue, or even aesthetics and fillers, or to reinforce after surgery tissues. And so that's been one of the directions. If you can create these hydrogel particles that form, you can kind of put as these kind of clusters of little spheres that are about the size of a cell. So you can imagine, if you imagine like packed gumballs all together, there's all these little holes in between the gumballs. And that's really important, so we can create like this type of pack of hydrogel particles in a wound. You have all these little holes so that cells can migrate in, and now they fill this space, and you can regenerate the tissue rather than having kind of scar formation. So I think there's applications in scaling up biological research in kind of these regenerative tissue engineering applications.
Scientists have known that circulating tumor cells in the bloodstream have the potential to provide vital information about a patient's specific cancer. But until research by your team, scientists and doctors could not reliably access information on how the cells behave. You and your team created a fast, effective mechanism to measure how these cells perform functions that drive the disease, such as producing proteins that degrade tissue. Tell us about this important research.
Yeah, and this is also, almost all of these, this is work that's collaborative across UCLA, which has been an amazing part of being part of this community. It's just so much high-level research across all different spaces. And this was a collaboration with Matt Redig's lab. He's in urology and works in prostate cancer. And also, I think Steve Dubinet's as well, and a few others. So,
Medicine.
Yeah. So it was a really collaborative effort where we had patient samples that we're getting. We look for, so let me first mention what circulating tumor cells are. So when we have a tumor, that tumor, when it becomes really dangerous is when it starts to metastasize, right? It goes to other parts of the body. And in that process, or one way that it does that is by releasing cells into the bloodstream. And if we can identify those cells, we call them circulating tumor cells. That's not a good sign if you have those, but if you can isolate them, you can start to perform what we call liquid biopsy. So we don't have to biopsy the tumor, we can take these cells from the blood to get information about the tumor. Right? So that's an advantage, and people have been starting to do this to look at genetic information about the tumor. But what we added on to that is, can we look at the functions of these tumor cells? In one particular function, these tumor cells that secrete enzymes that degrade tissue. Those are probably cells that are very dangerous because they can invade into tissue, right? And they can also cleave off parts of proteins on their surface that allow immune cells to recognize them. So we don't want those types of cells. And so we were able to kind of develop an assay that isolated these cells and then characterized their function, this protein cleaving function, and to categorize. We found that could help us categorize patients that were going to do poorly versus not poorly. Same. Yeah.
I see. So we've discussed the potential health benefits from your research. What would you say taxpayers received in return for this $15 million investment in your laboratory's research? It sounds like a really massive return in terms of economic, technological, and societal benefits.
Yeah, I mean, I think you're getting at the larger question, which is what is the value of research,
Right.
and how does that compare to other things that we could spend resources on? And I mean, to me, I think that, based on my personal experience, I will tell more about this, the value of research is a huge return on investment, right? It's not,
Yes.
You see some people say, oh, this is charity. You don't deserve these funds. And I almost kind of think, what are you talking about? I'm actually giving you more than you're giving me.
Yes, you are. Yes, you are.
I'm giving the public more, not you.
I mean, you're talking about benefits for
Right.
damaged heart muscle and for many diseases, prostate cancer and other cancers.
And so, of course, our work is applied, and so we can communicate that benefit to the public more easily. Of course, all the students that we train, it's been over 40 years or so, PhD students, many master students, 80 plus undergraduate students that we've trained. These are folks that are in industry, they're in other academic, that started their own companies. As you mentioned, 5 companies that raised other capital, hundreds of millions, 200 millions or so in capital, and have delivered products. So we didn't talk about it, but one of the products from the first companies, Cytovale, is a test for detecting sepsis when your immune system goes crazy on yourself.
Sure.
That's available in the hospitals in the emergency department, and it can give a result in less than 10 minutes.
Wow. Often deadly.
And deadly, right? And so every hour of delay is 7% increased mortality.
Wow.
Now, 50,000 or so of these tests have been given. Where are they starting? It's in hospitals in Louisiana, in Alabama, in Texas. Not in California. Hopefully, eventually in California.
Yeah, red states.
So, I mean, science is a world. It helps everyone, right? And you cannot separate it. And there has to be an understanding that what we do here is helping the public everywhere. And I think the return, that there's been, we were talking about it, was a $2.16. I think NIH, every dollar spent by NIH returns $2.16 or something like that. And that's what they can calculate, and then there's all the follow-on effects that are hard to calculate. But not to say that only applied research is valuable, right? I think you have to think about if we're not moving forward our knowledge in any discipline, what are we doing? What is the hope for the next generation if we're stopping at the current state and that we believe that's sufficient? I don't understand that. I don't understand how we can say that that's enough.
I mean, the human lifespan is so much longer than it was a century ago, less than a century ago. A lot of that is due to advances in medicine and technology. The federal government froze $584 million in research funds to UCLA, about 800 research projects, and has made deep cuts to the National Science Foundation, the National Institutes of Health. How is UCLA and how is science being impacted by the deep cuts in federal research funding?
Yeah, I think it's very personal, right? So, if you're somebody like me, I'll just talk my personal feelings first, and then I'll talk about students and other. Somebody like me who has the last 17 years I've been here at UCLA, really committed to trying to bring technologies out there to help the public to publish our work, share our findings with everyone. And then you get this response that just suddenly tomorrow your research is not valuable. That's the feeling that you get. And it's a exactly. It's this feeling of what is happening? Why is this happening? What did I do wrong? And
you didn't do anything.
I didn't do anything wrong. But that's the Kafkaesque aspect of this. I think everyone is feeling that. The students are feeling that, and so that's the first layer. Then you start to think. The next layer is, how can I trust this system anymore? Right? How the system has betrayed. This has been a system that has been around. Vannevar Bush, at least for science, the National Science Foundation, 75 years ago, there was this compact. Science, the Endless Frontier. If you haven't read that, it's a great manifesto on how we should think about the compact between the federal government and science research. And that, to me, it seemed like it was a no-brainer, right? That we would always continue that way. Now the question is, can we trust the federal government in the future? Can our students trust the federal government in the future? And to be part of this compact, to be working with us together, where we give our lives, our sweat equity to help the public in exchange for this kind of stable research environment. So I think we talked a little bit about this. The stability is really important for research, and if you start getting rid of that stability, that will change the next generation, how they think about where they look for, what kind of jobs they want to pursue. Do they want to go into an academic research type of world where there's so much instability? And I don't want to be a downer. So we're trying to do, what's the next step? We have to think about what's next, what comes next after this. But you also have to understand that maybe it's not the federal government that comes next, right? And so we have to be realistic as well and start to form new ways, a rebirth of what research enterprise looks like. Is it more and more interactions with industry? How do we build those interactions? Of course, they take time.
Yeah. It sounds like you're saying the answers to these questions are unclear.
They're unclear. We're going to continue to work on them.
Mm-hmm. What are your thoughts on the importance of basic research and what will be lost if the government funds applied research but not basic research?
Yeah. So this is really important in that I work at a lot of applied research, but a lot of the things even that we look at are discovered through serendipitous findings, right? Mm-hmm. So we try to do an experiment with a particular hypothesis in mind, and of course we find something that's completely opposite of that hypothesis, and we explore that route, right? That's like the basic research. That's like the fundamental aspect of it, is that you kind of go down the directions that you can. You lay the foundations for applied research, and I think there's that aspect, but there's also the aspect of we need to have some hope of the pursuit of knowledge itself is a valuable thing.
But not only that, I think you don't really know where the answers are going to come from. You can't just say, I'm going to go out and find a cure for prostate cancer or for heart disease. It may come from unexpected places. I think you've seen that through research.
Definitely, yeah. So, we've seen, we have some of the first things that led to the sepsis test. I was trying to do something completely different and put cells into channels and squish them against walls. And they ended up going to the center of the channel unexpectedly. And so then I had to look at all the basic research on what causes particles to focus in channels, and build off of that to really start to understand how to apply this. But yeah, the whole point is that you want to create this infrastructure of kind of catalog of different ideas that you can put together to be creative and innovative.
So maybe you've already answered this, but what's the impact of the uncertainty on young researchers? What are young scientists saying to you about whether they should continue?
This has happened now twice. I had an undergraduate, and I don't advise that many undergraduates. I've had undergraduates that have asked me about graduate schools outside the U.S. So ETH, Zurich, or EPFL, or places in the UK. Rather than, I've never had this happen before. They've always asked me about it. What about University of Washington or MIT or whatever? And now I have students asking about outside the U.S.
What do you say?
I say, EPFL is a great school. There's lots of good folks there that I know that it might be a good opportunity for you. I mean, you have to be honest.
You're in your early 20s now.
Yeah.
What do you think?
I think you explore all of your opportunities, right? So if you don't see opportunities here, you're going to explore opportunities outside the U.S. as well. And as a smart young person, you should do that. I guess I'm not saying that you should leave the U.S. I think it's about uncertainty, right?
Yes,
So if there's a lot of uncertainty, people are going to have many options on the table and find the ones that are more certain. And that's what's happening to our young folks now.
What do you think the impact will be if this uncertainty continues for another 3 years or longer?
So I think you're starting to see, I hate to be all negative, but...
Well, you talked about your important research. That was positive.
That's positive, okay. Yeah, so you're starting to see, and you're going to see more of this, is that faculty are going to leave the U.S. If you no longer have a capability to do your research here, they will find places that still value that. And there are places out, I was just in Japan, beautiful meeting, Science Technology Society Forum. The Emperor and Empress of Japan opened up the meeting to talk about how important science was. Can you imagine that happening here in the US? That our leaders would come and open up a scientific meeting.
And so what are your thoughts on the future of American research with deep federal funding cuts?
I think that we're all a really creative, innovative, hardworking group of folks that will find ways around these challenges. It won't be easy, and it will take time to make adjustments. Maybe like a hopeful thing here. So California has a new bill. If you're not aware about this, are you going to ask me?
The California Science and Health Research Bond Act?
That's right, yeah. So
tell us about that.
Okay, yeah, there's a new bond act. It's put in the state Senate by Scott Wiener in San Francisco. It's going to be voted on next year. It has to pass both the state Senate, the governor has to also be supportive, and then it's going to go to the public. It will be on the ballot. It will be similar to, if you're familiar with the CERM, California Regenerative Medicine Center, Institute for Regenerative Medicine. So that was supported by the public, and actually it was renewed. So the second the public renewed this. And so California was kind of one of the leading states. And Texas is another one that they have their own funding agency within the state. This would be beyond CERM, not just regenerative medicine, all science and biomedicine and environmental studies, etc. So I think very exciting. There's going to be a need to help push this forward. I'm trying to collect folks that are interested in helping across California, across the UCs. Maybe if anyone here is interested, feel free to email me. And so that we can, when we're ready, we can activate and start to really promote how important these types of things are.
So this California Science and Health Research Bond Act would create the California Foundation for Science and Health Research, backed by $23 billion in state bonds for peer review research support for life-saving research, medicine, climate, public health.
Exactly, yeah. So it would be like our own state NIH and NSF together. I think that will draw people from other states to California. I think that will, of course, we know that the investment in science pays dividends. So especially if that stays in California, although we see some of our work goes out and helps Alabama and Louisiana. So, which is fine, I'm happy with that. So I think, it's about goodwill in the end. So now, this leads to kind of another related question, which is, at some point, if we lose trust in the federal government, so should some of those funds that we're sending to the federal government come back to support these efforts at the state level? And that might be a new conversation that will start to happen.
What advice do you give to students both on these questions that you've been discussing, but also students who want to have both academic and entrepreneurial impact?
Yeah, I think I think the biggest advice I give to my students is that they have to work with others. Right? That this is
You've done that throughout
yeah,
your career?
exactly. Yeah, talk to the doctors, talk to the patients, talk to everyone. Talk to the customers. Right. So I think this is the key thing to really have impactful work. What I share to my students, at least that's been our secret sauce, is really to build teams, build collaborations, understand the problems, and then you're solving problems that somebody cares about, at least one person.
And now let's take your questions. Who'd like to start? Okay.
Here we are, Stuart.
Michael Goldstein.
Thank you.
Try this one.
Great, thank you for your comments. I agree 100% with everything that you said, and I imagine that almost everybody in this room agrees with you 100% in terms of what you said. But the people in this room are not the problem.
That's right.
It's the people outside of this room. And what you described is not just the case with scientific research, but it's the case with everything that the university does, and it's really the case with the whole notion of rationality itself being questioned. So my question for you is this: when you think about, not personally, but when you think about research scientists, medical scientists, academics, do you think there's anything that they've done over the past couple of decades that has actually created, and in your remarks you blame the federal government, and of course we're all on your side on that, but I think there's something wider in the culture as well. Can you think of things that people in positions of, you might say, leaders of rationality have done in the way they've presented themselves and their issues over the past decades that have actually made the situation worse?
It's a great question. It's how do we communicate the value of rationality, right? And where have we gone wrong? And I think that there's several trends that are happening simultaneously. One is the ability for anyone.
Ouch. My apologies. Carry on. Don't get them too close together.
I think one is the ability for anyone to be an expert through social media. And so what that does is it dilutes real experts, right? So everyone's an expert, no one's an expert. And so then the public starts to not know what is rational, what is not rational. And everyone has their own incentives. The social media algorithms have their own incentives, they want your attention. And that starts to dominate the discussion rather than what is actually rational. So I think that's one trend that's happening. I think that the COVID pandemic was a challenge for, even though actually science, there was a triumph for science, in my opinion, it was a triumph for science. We had vaccines that were developed in less than a year. Can you believe that? That's like unheard of. We had diagnostics that came in 6 months. So these are, it's phenomenal. And that was not talked about though. Those wins for scientists and for rational thinkers were not discussed at all. Were not, and also in fact turned around. The vaccine were turned around as like a Bill Gates swine virus or something, right? And so like it was, I don't know, like that was something that, I don't know, the communication aspect. Maybe Stuart has a better answer for this. Like how do we improve the communication of all the things that science is doing?
The problem is it was a novel. It was something novel, and so the thing is, early on, we didn't know very much. But science is a process, and so the thing is, you learn. But I think people don't understand probability, and they don't understand the way science works. That early on, we didn't know if masks were needed. We didn't have a vaccine early on.
Definitely the expert opinion changed rapidly at the beginning, right? People were wear masks, don't wear masks.
And scientists get smarter as time goes on, as you learn more. Who else?
Thank you for your talk. When you began your discussion about Lyme disease, which was fascinating, you stated the CDC recommends. So what are we going to do now? Is this new idea of a state consortium of scientists going to be the go-to recommends? Who's going to recommend?
Yeah, that's a great question. This was the old CDC, so still, I think we still had some trust. Now who knows with the new CDC, right? So, I think this is I was talking about this trend to defederalization. I think that we'll see that actually these types of functions that were happening at the federal level are going to happen at the state level, and because that's where we'll have trust, right? I think CDC is just going to be one of many agencies where that starts to happen. I think that it has to be that way.
Are there other questions? Okay.
Thank you. It's a great talk. Thank you. Can you say a little bit about how a scientist, an engineer, goes from the lab where you've been trained, to discover things, to solve problems, to a business? How does one person, and this may be part of the team approach, but can you just talk a little bit about that? Because it's such a different way of thinking and working.
To 5 businesses.
I think your question is not like starting up companies, but like how do I approach, or maybe it is, but it was. Okay. the other question is like many of us are trained to write grants. We're good at writing grants and then receiving funds and then conducting the research, writing papers, repeat, right? And we're not trained at talking to companies to try to get them to fund our research. And that's a whole new skill set that we'll have to learn. But I think we will have to learn that skill set. And maybe as a university, we should be thinking about ways that we can help our young faculty to learn those skill sets too. So that's one aspect of like maybe talking to larger companies. And I'm not saying I'm very good at it. I've been negotiating with some of our local pharma companies to get some resources, and we'll continue doing that. Now, to start small business or startups, right? So, it's one of those things where I think naivete as a young faculty member just said, let me just do this. Let's just start the process. I don't know how hard it's going to be. I don't know how long it's going to take. I don't know how much burden it will be on my family and my wife. And then you find out. I think that you don't start these things unless you don't know. Maybe my wife can comment on that. So the first company that we started, she's welcome to comment, but the first company that we started, 10 plus years before we had a product that was FDA cleared. So that's a decade of work. We did not tell the first investors that this is going to be 10 years later that you're going to get, we didn't think it ourselves.
Research takes longer than you think, right?
So you start doing it, and then, I think once you've done it once, the next time is easier, and then the next time is easier, and the next time is easier. And then we have a network of folks. UCLA has also a great network of folks that have done this, that the next group, the next young generation can talk to.
Any final questions? Okay.
Would you
Political
say-
science.
Yeah, well, would you say a little bit more about the exit option? I do some work with the European Research Council, and they're talking about shoveling in money and trying to bring whole labs over from the US to Europe. What's your perspective on that?
Yeah, I think that there will be some labs that will have to do that because they can no longer function with the current environment. And there will be other labs that will find other ways, and there will be other labs that decrease their activity level. And I think there will be different ways that people will evolve to the current state of things. But the current state of things is political appointees picking which grants are going to be funded. Grants?
Do you have any concluding comments for us?
I want to be positive, so maybe the concluding comments are there's a lot of hope. I think the state of California is a great state to be in. The and I think having a goodwill of what we want to achieve, working together, I think we can do a lot more, and we can overcome these federal challenges. Thank you.
Dr. Dino Di Carlo, thank you.